In this video, we will do a streetlight and shadow example. So this is problem number 5 from worksheet 8, and it says that a 6-foot man is 10 feet away from a 20-foot streetlight. He's walking away from the streetlight at a rate of 3 feet per second. Part A asks, find the rate at which the length of his shadow created from the streetlight is increasing. B asks, find how fast the tip of his shadow is moving along the ground. So first, pause this for 6 minutes to try it. 4, 3, 2, 1. Pause it for 6 minutes and try this. All right, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it. So let's start with A. And so I'm going to begin by drawing a picture. So I could draw the ground, and then we have the street light. Okay, so I'm going to draw kind of a post. And at the top of the post, we'll have this light. Okay, so this light is kind of emanating. All right, so we have the street light, and then some distance away from the street light, there's this person, there's this man. So I'm gonna just draw a stick figure. Okay, so we have this man who's standing some distance away. Okay, and then it talks about the shadow that's created from the street light. So the way the shadow gets created is, the light that travels like this and it touches the very tip of this person's head like that is not going to be blocked off by the person. Any other ray of light that goes from the lamppost hits the person like this, that would be part of the shadow. But this line that doesn't really touch them, that's just kind of like that, this is all going to be seen here. This part's going to be seen. So the shadow is here. That is the shadow from that light. And that length from the person to this tip, here's the tip of the shadow, that's changing. So I'm going to call that length X. Okay. Another length that's changing in this picture is the distance from the street light to the person, because it says the person is walking away. So I'm going to assign a variable to that. Anything that's changing, I should assign a variable to. So I'll call that Y. But there are a couple of quantities here that are constant. Like it says the street light is 20 feet, which means that it's 20 feet tall. So the height of the street light is 20 feet. And it says the 6-foot man, so that means the height of the person is 6 feet. All right, so let's now write down the rates that we know and want to find, because I got my picture, I got some variables assigned. So what I know, what I'm told about this, is the rate at which this person is walking. They're walking away from the street light at a rate of 3 feet per second. So that tells me how fast Y is changing. So I know dy dt is going to be positive 3, and it's positive because Y is increasing, because he's walking away. If he was walking towards the street light, I would have written negative 3. Okay, and I want to find, let's see, part A asks me to find the rate at which the length of his shadow is increasing. So the shadow length is described by the variable x. So I want to find dx dt, and I want to find dx dt in part A. All right, so now we need to set up an equation. And based off of my picture, I see this is a right angle and this is a right angle. And if I look at the small triangle and the big triangle that we have, they are similar. Oh, we got some similar triangles. Okay, to have similar triangles, I just need to show that they have 2 pairs of angles that are the same, because if I can show that 2 pairs are the same, that has to mean that the third pair is the same. Okay, so if I draw the small right triangle, this is x, and that's 6. And if I draw the big right triangle, the base is x plus y. Here's my right angle, and the height is the 20. Okay, so both the big one and the small one have a right angle. That's one pair that's the same. They both share this angle. Both of them have that small angle. And now that shows that they have 2 pairs of angles that are the same. That will automatically guarantee that this third angle, the third pair of angles, are the same. So these two are going to be the same as well. All right, and as we've seen before, when we have similar triangles, our equation can come from a proportion that we set up. So in the small triangle, if I set up the proportion x over 6, that ratio, that's going to be equal to the ratio, the same corresponding ratio in the big triangle. So the x corresponds to x plus y in the big triangle, and the 6 corresponds to 20 in the big triangle. Let's simplify this a little bit. I can cross multiply to get 20x equals 6 times x plus y, and this is 20x equals 6x plus 6y. And if I subtract 6x, we get 14x equals 6y. So it helps to simplify it a little bit because now the fraction's gone. This is very simple. Okay, now we're ready to take the derivative. So we take d dt of both sides. So when we're doing these related rates questions, we do d dt. The other way I can tell I need to do d dt is because we already identified that we know dy dt, and when we want to find dx dt, and both of those are a d something dt. Okay, so from here, the left-hand side, I need the derivative of 14x. The right-hand side is going to be the derivative of 6y. Now this is just an implicit differentiation. So the 14 will stay multiplying the derivative of x, which I would write as dx dt, because these variables are different. And on the right-hand side, we'll get 6 times derivative of y is dy dt. All right, so now let's plug in for what we know. We know dy dt is 3. So we get 14 times dx dt equals 6 times we know dy dt is 3. All right, so if I divide by 14, we get dx dt equals 18 over 14. And I can simplify this to be 9 over 7. And the units of the x on the top, so x is a length, and the units of length in this problem were feet. And for t, it's the units of time, and in this problem, the units of time were seconds. Okay, so this is dx dt, and that was the rate at which the length of the shadow was changing. And in this case, because that was a positive number, it's telling me that the shadow length is increasing at a rate of 9 over 7 feet per second. So now we're ready for part B, finding how fast the tip of the shadow is moving along the ground. So B, we want to find the rate at which just the tip of the shadow moves. So at first glance, it might be like, wait, isn't this just the same thing that we got in part A? Isn't how fast the tip of the shadow is moving along the ground? Isn't that just the same thing as the rate at which the length of the shadow is changing? But it turns out it's not, because the length of the shadow is dictated by two things. It's dictated by how fast is the tip moving, but also how fast is the person moving, because both of them are moving to the left. Okay, part B is just asking, well, how fast is the tip moving? And that's going to be dictated by two things, because as the person walks away from the street light, y is changing in length, and x, the shadow, is changing in length. I need to add up those two rates to figure out, how is this distance changing? Because that distance is dictating, how fast is just the tip moving. All right, so the rate at which the tip of the shadow moves is going to be dx dt plus dy dt. All right, and dx dt, that's what we just figured out. That's 9 over 7. dy dt is the rate at which the person is moving, and that was 3. And if we add these and get a common denominator, we will end up with 30 over 7 feet per second. And that's our answer.